Hello, everyone. I am Quintarius Moore. Thank you for attending my virtual talk. Today, I will be presenting the work that has been undertaken throughout my time as a Department of Energy Computational Science Fellowship Fellow. Many thanks to my research advisor, Dr. James Batiste. I will give an overview of our work in the modulation of the electronic structure and chemical reactivity of 2D materials by the application of strain. We will journey through a quick introduction and outline our motivation and challenges and a bit about mechanical chemistry. And we'll discuss two of the research components of our work. One, looking at the chemical reactivity of graphene in the presence of an diazonium and how the application of strain influences that reactivity. And also looking at tuning the electronic and chemical properties of strain MOS2 in the presence of reactive species. And we'll wrap up our discussion with a quick summary and brief acknowledgements. So two-dimensional materials have attracted tremendous research interest since the breakthrough of graphene. The family of 2D materials encompasses a wide selection of compositions, including most elements of the periodic table. And this derives into a rich variety of electronic properties, including metals, semi-metals, insulators, and semiconductors. Their atomic thickness and exposed huge surface even make them highly designable and manipulatable, leading to the extensive application potentials in next-generation circuits, sensors, and tribological applications. Also, some 2D materials have a very low frictional coefficient, which makes them an appealing solid lubricant for use in satellites and other aerospace applications where liquid lubricants are infeasible. However, exposure to environmental species such as oxygen and water has been shown to degrade the lubricating properties of these materials, limiting their usefulness for many potential applications. And the precise mechanisms of these interactions and how they degrade tribological performance, however, still remain poorly understood. And so one material of interest to us is graphene, and as in a single atomic plane of carbon, graphene can be wrapped up into other graphitic materials, such as fullerene, carbon nanotubes, and thin graphene films. And so you just think of graphene as a single layer of graphite, which can be found in pencils. Due to the internal exceptionally high crystal quality and electronic properties, monolayer graphene exhibits remarkable optical, thermal, and frictional properties. And our next 2D material of interest is molybdenum disulfide, and it's in the family of transition metal dichalcogenides. In contrast to graphene, a monolayer of MOS2 consists of an atomic plane of molybdenum atoms sandwiched between two planes of sulfur atoms. Interestingly, there exist two phases of MOS2 that only differ by slight rotations of the bottom sulfur atoms, 1T and the more stable 1H phase. And this slight change in structure yields quite different properties, with 1T phase being metallic. And in general, MOS2 has remarkable properties that lend towards its application in electronics and as a solid lubricant. The aforementioned applications are realized or degraded by the modification of 2D materials on the basis of modulations, during which specified types of disorders are quantitatively created for altering the crystal structure and consequently obtaining or diminishing the wanted properties. And the difficulty lies in being able to selectively initiate and control functionalization and wear of the surface. We have seen that modifications in properties of 2D materials have been realized through strain from exfoliation or synthesis on various substrates, strain in the form of bending, wrinkling, and stretching. Therefore, having a good fundamental understanding and control of the strain structure and structure property relationship is necessary for selective and controlled modification. And so we seek to realize these specific and precise distortions by force to selectively functionalize the surface of 2D materials. And we do this by the use of mechanical force to direct and control chemical reactions. And now, the effects of light, electric charge, and heat on chemical reactivity are well understood. However, the effect of mechanical force is far less developed. And so in our work, the broader impacts would be to contribute to new, sustainable, safer, and cheaper chemical synthesis, and also the widespread appreciation of mechanical chemistry as a discipline. And so the goal of our overarching goal of our work is to gain a fundamental understanding of using geometric distortions to influence chemical reactivity. And we've divided these into two main questions for our projects. One, how does varying mechanical strain of the graphene lattice affect the reactivity of graphene? Two, how does controlled strain influence the reactivity of MOS2 on metal substrates? Now we shall venture through our research efforts on the radical reaction of 4-nitrobenzene diazonium, 4-NBD, with graphene, where out-of-plane distortion should drive carbon-carbon bond formation. And so literature shows a relationship between strain and formation energy. And in this first work reference here, tensile strain was applied to a substrate with graphene mechanically exfoliated to the surface. And it's been demonstrated that with an increase in strain, a decrease in formation energy was observed. And this decrease in formation energy means that less energy is needed to initiate this reaction. Also, it should be noted that in this experiment, wrinkles were also present during this tensile strain experiment due to slippage between graphene and the substrate, since tensile strain was actually applied to the substrate and not directly to graphene. And in this next work, the researchers looked at chemical reaction of strained graphene islands on different copper 111 foils. And so they've shown that single crystal copper induces more compressive strain in graphene due to lattice mismatch. And it's seen that this increase in strain has led to an increase in reactivity indicated by the intensity in D peak from the Raman spectroscopy in comparison to the non-existent D peak shown with graphene transferred onto polycrystalline copper. But also it should be noted that the metal introduces electron density to graphene, and this electronic effect may affect the reactivity of graphene as well, and not just the compressive strain. And so in our work, we seek to systematically control the strain applied to graphene, and we hypothesize that the true strain that induces an increase in reactivity is actually caused by out-of-plane strain, which mechanically forces graphene to a structure that more so resembles the product state after chemical functionalization. And as I mentioned, the product state here in our model is the reaction of 4-NBD with graphene, and we visualize the relaxed geometry of the product state of our test system. And we use density functional theory and molecular dynamics to calculate these structures and energetics. And we used high performance computing from San Diego National Laboratories and the computing cluster at my home university, Texas A&M. And in our work, we experimentally and computationally determined the effect of curvature on the reactivity of graphene. And so to control the extent of out-of-plane strain in graphene, we transfer graphene to both flat silica films and silica films consisting of 6 nanometer or 85 nanometer nanoparticles, seen in figure A and B. The smaller nanoparticles, the greater the adhesion of the graphene film, leading to greater curvature and increased lattice strain. Reacting these samples with 4-NBD led to an increasing Raman intensity of D and G ratio, indicated by an increase of sp3 character induced by the introduction of covalent bonds, which can be seen in panel C. So the bright areas show an increase in this D to G peak ratio. And also from panel D, graphene on the smaller nanoparticles reacted to a greater extent than graphene on both the larger nanoparticles and flat silica, which had a similar extent of reactivity. And so moving on to the computational side of this project, we use molecular dynamics. Using molecular dynamics, curvatures at and between our experimental cases were created to understand the structure-activity relationship. Now, density functional theory was used to calculate the energetics of these structures and curvatures in between to understand the reaction energetics between 4-MBD and varying curved graphene. We also developed a theoretical model based on the pi-orbital axis vector, POAV, method to quantify the effect of curvature on the orientation of the graphene 2pz orbital. We determined that the curvature affects the in-plane electron delocalization and increases the electron availability for out-of-plane functionalization, shown in figure B, indicating an increased thermodynamic preference for 4-MBD reactivity to greater curved graphene. And so just to reiterate, experimentally and computationally, we determined that controlled out-of-plane strain can be applied to graphene, and we see that with increasing curvature, this disrupts the in-plane delocalization of graphene, yielding a decrease in the activation barrier of the test reaction as a function of increasing curvature. Next, let's explore ongoing work studying strain and its effect on the reactivity of MOS2 in the presence of environmental reactive species. And so in our lab, Dr. Fenglu Wu developed a mechanical exfoliation technique that allows for the transfer of single layer MOS2 onto the surface of gold 111. Through characterization, it was seen that a coherent heterostructure of monolayer MOS2 was intact. The 1H and 1T phase were coherently shown on gold 111 surface. And we use scanning tunneling spectroscopy to confirm the presence of the two phases and computational models to replicate the moire patterns of the two phases. Here we see that the periodicity and structure of the simulated patterns are similar to those observed in the scanning tunneling microscopy image. In addition, the rotational angle between the two moire patterns closely match our experimental STM data. We believe that this formation is likely due to charge transfer between the metal substrate and also built-in tensile strain in MOS2 during the transfer. More of our research interests and in collaboration with Sandia National Laboratories deals with the reactivity of MOS2 in the presence of an oxidative environment, as seen on such as the RAM face of the International Space Station, and how that affects frictional performance and wear and tear of the material. We take it a bit further through our collaboration to study not just how pressure and temperature affect the reactivity, we study the role that defects play in increasing reactivity. But since in application MOS2 is applied to a metal surface, we also seek to understand how metal substrates affect reactivity through electronic effects and strain. Also, the extent to which layer thickness affects these substrates of effects. Lastly, controlling the mechanical force on MOS2 to induce out-of-plane strain to determine how the disruption of local orbitals affects the reactivity of MOS2 as well. And so we are continuing to work on describing the absorption of water and oxygen on MOS2 and their effects on the tribological properties. And so I hope that you all have learned a bit about how we utilize mechanochemistry and how that can be used to study the effect of strain on the reactivity of 2D materials for the selective functionalization and to understand the mechanisms of oxidation and disruption of tribological performance. We will now conclude our journey with a brief summary and acknowledgments. And so just to reiterate, experimentally and computationally, we determined that controlled out-of-plane strain can be applied to graphene, and we see that with increasing curvature, this disrupts the in-plane delocalization of graphene, yielding a decrease in the activation barrier of our test reactions as a function of increasing curvature. And we are continuing to work on describing the absorption of water and oxygen on MOS2 and their effects on tribological properties. And we postulate that new science may be pushed forward by investigating changes in reactivity of 2D materials as a function of precise out-of-plane distortion using mechanical force to the basal plane. And so I would like to thank my research group and committee members at Texas A&M and my research advisor, Dr. James Batiste. I would like to thank friends and mentors from Texas State University for the continuing support throughout my journey, and also our collaborators at Sandia National Laboratories, Dr. Sandros, Dr. John F. Curry, Dr. Arjabe, and especially Dr. Michael Wolf, our coordinator, and also team members from the Center for Mechanical Chemistry at UPenn. And lastly, I'd like to thank you for the support from the CSGF, which gave a unique opportunity to me to explore this work, and I am very grateful for the support of CSGF. And I look forward to a lifelong connection and giving alumni support back to the CSGF. Thank you so much for your time. I will take any questions at this time. Thank you.